Okay, that's an example in a one-dimensional state space. Let's look at a two-dimensional example. And let's go back to our favorite example of shark-tuna space and of the shark-tuna differential equation. And we would like to understand the behavior of this system. And of course, it's completely not obvious by staring at the equations. So we're going to make state space. State space in this case is going to be the two-dimensional non-negative space ST, where a point ST represents a certain number of sharks and a certain number of tuna. So for this very simple example, let's start with the point 5, 5. So that's S equals 5, T equals 5. And we would like to see what the change vector is at that point. So at that point, we know that S prime, just plugging 5 and 5 in for S and T, S prime equals 25 minus 5, or 20. T prime equals minus 25 plus 5, which is minus 20. So we have a change vector. The S change vector is plus 20. The T change vector is minus 20. And the resulting change vector, which is the sum of those two, is going to look like that. I want to correct a misimpression that I may have given. We were at the point 5, 5, which is right there. And we calculated the change vector, and if you remember, S prime is 20, and T prime is minus 20. And so let's construct that change vector. The S prime change vector has to be 20 units long, and if this is 5, then that's 10, 15, 20. So the resulting change vector is that long. It's plus 20 in the S direction. The change vector in the T direction is minus 20. And so the first thing we have to do is create this negative t-axis, where this is minus 5, minus 10, minus 15, minus 20. And the t prime change vector is then this vector pointing in the negative t direction and having length 20. And then, of course, the resulting net change vector is right here. And this is the change vector S prime T prime at the point ST equals 5, 5. Now, that said, you might ask the following question. This is a big change vector pointing here, and it's pointing us into negative t space, which we said is la-la land. It does not exist. So how is that possible? Is that a problem? And the answer is no, it's not a problem, because this very large change vector tells you where you would end up if you followed it for a long time, one whole time unit. But we're not going to do that. What you're going to see is we're going to be following those change vectors for very, very short times. And so we will never go so far as to plunge into la-la land following that change vector. And that's going to be our change vector at the point 5, 5. Let's take another point. Let's take the point 6, 2, right there. So at the point 6, 2, what is the change vector? The change vector is S prime. So what do we have here? We have 6, 2. So S equals 6, T equals 2. ST is 12. Minus S is 12 minus 6, or 6. And T prime is equal to minus 12 minus ST plus T, which is 2, is minus 10. So now we're going to need a change vector of plus 6 in the S direction and minus 10 in the T direction, and that's going to look like that. Now, it may look like those vectors are plunging into non-existent territory of negative tuna, but they're not, because this is the change vector at that point. What we will find is that as we choose points down here, which are very close to the boundary, we will start to see that the change vectors start to turn. And they turn like this. And if we keep calculating the change vectors, we will see that the change vectors, in fact, are suggesting a cyclical motion. And that if we calculate this change vector here, and this change vector here, and this change vector here, we will see that the change vectors move around in a circular fashion, suggesting the oscillatory populations of sharks and tuna that we saw from the simulation when we first played with that model. There's a very general point that I have to make here, because I have a feeling something might be bothering you, which has to do with these kinds of models in general. We have very, very small points here. And let's say this point is S equals 0.02, T equals 0.04. Now, you might reasonably ask an almost philosophical question, which is, what does that mean? What does S equal 0.02? What are 2/100ths of a shark? What does that mean? You would be forgiven for saying 0.02 sharks. That's not a shark, that's sushi. What meaning can we give to that fraction of an animal? And when we deal with models of susceptible and infected people interacting in epidemiology, we will have situations where there are 10 to the minus 3 people left. And you have to ask, what is 1,000th of a person? So this is a philosophical problem which is encountered by a lot of models and a lot of sciences. And here's how we deal with it. We deal with it by pretending that the numbers are so large that we can approximate it with a continuous variable. That we're not going to worry too much about what it means to say 1,762.4 sharks. We're going to pretend that that's a good number, and we're going to deal with it. We're going to pretend that this is a smooth quantity, even though the number of sharks is in fact an integer. Now you say, well, is that a good approximation? Let me remind you that in chemistry, we deal with a situation where we have sodium ions and we have chlorine ions, and they run around in the solution and they bump into each other, and we make equations for how the sodium concentration changes and how the chloride concentration changes. But remember that the number of sodium ions in a milliliter of solution is an integer. And the number of chloride ions is an integer. it's a very large integer. It's like 10 to the 23rd, but it's not 10 to the 23rd 0.5 because these are whole objects and they are represented as integers. But in chemistry, the integers are so large, the number of sodium ions and chloride ions are so large that it's perfectly okay to approximate that with a smoothly changing variable. And we do make the same assumption in standard population ecology and in standard epidemiology, the spread of diseases. Now, that said, if there are situations where your ecosystem truly has one shark and two tuna, this is not a good model for that system. Don't use this whole modeling approach because the situation has evolved to a point with so few objects that you can't use the continuous approximation anymore. You need to go to a completely different style of modeling for when you have very, very tiny populations. And by the way, the same thing is true in chemistry. If you have 2 sodium ions and 3 chloride ions in your beaker, you cannot write Na plus Cl goes to anything because it isn't going to go to anything because the sodium ions are never going to find the chlorine ions. So in many of these subjects, we make this assumption of continuity to make this kind of modeling possible. And what that means is that these models really are restricted to fairly large numbers of animals. And you can think of S&T now not as number of animals, but maybe millions of animals. So in that case, in both of these situations, we make the assumption of continuity, which makes this kind of modeling possible. Just to wrap this up and to give you some terminology to talk about this stuff, we've been talking about these things which we have been calling change equations. And the change equation is x prime equals some function of x and y, and the y change is some other function of x and y. And that's our change equation. Now, just to give you a little terminology, the official name is not change equations. These have an official, fancy, mathematical name, and we might as well use it. They're called differential equations. So our whole course is a course in differential equations and their applications in biology. And that's what we're going to call, this is what we're going to call it from now on, because that's actually the technically correct name and also connects you to the literature. If you go and tell people you're studying change equations, they're not going to know what you mean. But if you tell them you're studying differential equations, everybody knows what you mean. Now, when I talk about these differential equations, there's a very important point that I want to make, which is I sometimes make it very paradoxically by saying differential equations are not equations. What do I mean by that? Well, we can write down, you know, x prime equals f of xy. And there is an equal sign there, and you can say, well, isn't that an equation? But the thing I want to stress is we're not going to be viewing this as an equation. We're not going to be subtracting something x from both sides. We're not going to be substituting y squared for x. We're not going to be banging on this thing and moving terms around and operating with this thing the way we have learned to operate on equations with substitutions and taking the square root of both sides and all of that stuff. Not going to be doing any of that. The only purpose of this expression, x prime equals f of xy, is that if you plug in an x0 and a y0, this is going to give you x prime at 0, and the y prime equation is g of xy. When you plug in x0 and y0, it's going to give you y prime at that 0. And the x0 prime and the y0 prime, those are the changes at the point x0, y0. In other words, this equation, we're not going to view it as a piece of language that we're going to manipulate. The differential equation is a machine for spitting out change vectors. And that's the only way we're going to use it, and that's the only way we're going to view it. It's a recipe for generating change arrows or change vectors at any point by plugging the point value in and getting the changes. So it really is a machine where you plug in your state and it gives you your change of state. Therefore, it's a much better view of this differential equation to not view it as an equation at all, but to view it as a function v from state space, which is in this case ST, into another space, which is the space spanned by S prime and T prime. It's the space of changes. It's change vector space, if you will, not state space. And this change vector space has its own name. It's called tangent space. So the proper way to view a differential equation is as a function from state space into tangent space, where you plug in S and T into the function, and the function spits out S prime and T prime. So in this case, state space ST is going to be R2, that is the set of all pairs, as we learned last week, the set of all pairs in R, and of course it's going to be R2 greater than or equal to 0 for both of those, that is to say the non-negative quadrant of R squared. And then tangent space is going to be another copy of R squared. Not the same copy, because the units here are different from the units here. The units here are in animals, and the units here are in animals per unit time. The vectors here are always positive or 0, but the vectors here can be negative if the change is negative. So V takes R squared into R squared is the way to look at this differential equation as a function from state space into tangent space. And in that context, this has a fancy name in math. It's called a vector field. And so when we study differential equations, we're merely using the differential equation to set up the vector field. And the vector field is going to tell us how things flow. And this is how we're going to use this differential equation. This is really better seen as a function that assigns change vectors to every point in state space.